So there's this other small YouTube channel you might not have seen. Wait, no, not him. Fieldhouse Engineering. They run a series of challenges for engineer and maker types. Fieldhouse Challenges. It has been suggested I might like to enter, and though I've watched the last couple with interest, I've not felt compelled to take part. Until the most recent challenge, which is slightly different to the others, and appeals to me for some reason, even though I've never built anything like this before. The challenge is quite simple. Build a device to throw an egg as far as possible. It must weigh no more than 3 kilograms and fit inside a 300mm box. The only energy source allowed is gravitational potential energy, i.e. a weight raised to a height. This is more or less the definition of a classic trebuchet, though the rules do allow for some variation. For example, the energy can change form before being delivered to the egg. But I like the straightforward nature of this challenge, so I'm going to base my entry on the simple trebuchet design. First things first, within the limitations of the rules, how practical is the challenge? If I were to raise a 3 kilogram weight by 300mm, that equates to 8.8 joules of energy. If an egg weighs 60 grams and all that stored energy is converted into kinetic energy, that's enough to propel it at a speed of 17 meters per second. And if launched at an optimum angle of 45 degrees, that would throw it a distance of 30 meters. Of course, that wouldn't be achievable in reality. The weight couldn't use all of the 3 kilograms, or there would be nothing left for the structure of the trebuchet. I also couldn't raise it the whole 300mm unless it had zero height. And it wouldn't be possible to convert 100% of the stored energy into kinetic energy, since there are always losses. So in the real world, the best I could probably hope for would be somewhat less than half of this 30 meters. But that at least gives me something to aim for. The classic trebuchet has been refined over hundreds of years through a process of trial and error, and some general design guidelines have emerged. A heavy counterweight is attached to the short end of an arm. The projectile is attached, usually on a sling, to the long end of the same arm, which rotates about a pivot. It's generally agreed that the long end of the arm should be around 5 times longer than the short end. This straight away poses a problem. To fit inside the box, the short end of the arm would have to be less than 70mm long, making the usable drop of the counterweight only about 100mm. By the way, yes, the arm can go outside of the box after the trebuchet is fired. It also seems to be a rule of thumb that the counterweight must be at least 100 times the mass of the projectile. For a 60-gram egg, that would mean a 6 kilogram counterweight, which is twice the mass allowed for the entire machine. So it's clear a traditional trebuchet design is not going to work. It needs a bit of creative re-engineering to make the most of the limitations of the challenge. So I came up with this. This is my proof of concept prototype. I've split the long arm into 2 arms and flipped one round to fit in the space allowed. They are linked with pulleys and a steel cable. I'm using barbell weights temporarily, which are far too big, and there's no trigger mechanism yet, so I'm just letting it go with my finger. This is my first test shot. Just over 7 meters. Wait a minute, that's not an egg. It's a potato. This potato weighs the same as an egg and is much more likely to survive the experience. So for the time being, this will be the egg's stunt double. The trebuchet is currently screwed to this heavy wooden block, which helps stability, but it's far heavier than the rules allow. So I'll need to build a proper frame. I built it from aluminium tube to keep the weight down, and even drilled holes to lighten it further. The less the frame weighs, the more the counterweight can weigh, which equates to more stored energy. Here's the second version. Note that I've also put wheels on it. The wheels on a trebuchet aren't just for transporting it to the battlefield. They serve another important function. They allow the whole trebuchet to roll back and forth during firing, allowing the heavy counterweight to fall directly downwards, instead of in an arc. This improves the energy transfer, as energy isn't wasted moving the counterweight back and forth. Here I'm using 2.5 kilograms of counterweights, raised to a height of 250 millimeters, and everything else weighs less than 500 grams. I've also included a proper trigger. Perhaps more complicated than it needs to be, but it ensures only a light pull is required to fire the trebuchet. That was only 6 meters, less than before. It's obvious screwing it to the wooden block provided an advantage. But there's a lot wrong with the trebuchet that hopefully I can improve. The wheels seem to be doing their job. The weight falls vertically, but it clearly lands with a lot of force, which is wasted energy not being transferred to the projectile. The frame is also jumping high in the air, affecting the shot and wasting more energy. And after release, the end of the arm keeps moving until it hits the ground, risking altering the position of the release hook. The angle of this hook is vital to ensure the loop slips off at the correct moment for the best trajectory. So I made some improvements, starting with replacing the large diameter barbell weights with these steel bars. These weigh the same but take up less vertical height. I also added another cable and spring to catch the arm and stop it slamming into the floor. Well, that didn't work. It jumped even higher in the air and the end of the arm still hit the floor. I've put as much mass as possible into the counterweight, but now the frame is too light and it won't stay on the ground. I need to work out how to hold it down somehow. I tried adding a G-clamp to the front to see what happens. The clamp weighs 1.5 kilograms. This takes it well over the weight limit and wouldn't be allowed. That was much more stable, but it released too late as the hook is now in the wrong position. I made some adjustments and tried again. Misfire. There isn't a proper place yet to hold the projectile, so I'm just balancing it on the narrow frame. The potato fell off and got wedged against the diagonal strut. A good stable shot, the best yet. That was 9 meters. But obviously I won't be able to use the G-clamp, so I'll have to find another way. By this stage, my potato was starting to get a bit squashy. Time for a real egg, made out of real plastic. It's the same size and shape as an egg, but as the plastic is more dense, it would be heavier. So I drilled a hole in the center to remove some weight. I also added a proper shelf to hold the egg. still around 6 meters. The egg doesn't seem any more aerodynamic than the potato. I tried making various adjustments to the length of the sling and the angle of the release hook. But I still couldn't do better than 6 meters. So then I tried moving some of the mass from the counterweight to the frame. This will reduce the energy available, but should result in a more stable launch without exceeding the 3 kilograms total weight limit. But this only decreased the range further to around 5 meters. One thing I had wanted to try was to replace one of the pulleys with a cam, similar to those on compound bows, to control the rate at which the energy is transferred to the arm. But it seems whatever I try to increase the range, it just ends up throwing the frame further in the opposite direction. Maybe 6 meters is the practical limit of this design, within the weight and size permitted. So, do I think it's in with a chance of winning the competition? No. In fact, I'm not even going to enter it. I'm no trebuchet expert, but I can't help thinking it should be possible to do better than this. And all along I've had a niggling feeling that maybe there's a better way. Based on this.
Gravitational potential energy can change into a different energy store after the trigger pin is pulled.
Maybe there's a way of exploiting this rule to get better performance. So I came up with this. But to see that, you'll have to watch part 2.